So chapter 7, we're going to start working with another function family. This time it's the exponential function. And you'll see here that I've written the pattern for the exponential function out for you. All of these functions have a pattern, of course. And this one, it takes the form y equals a b to the x power. So we're going to be dealing with exponents, which is why it's called the exponential function. So if you notice there, the x, which is the independent variable, that's what we're going to be evaluating our function for. Okay, so we're going to be changing the value of x and determining what y will be in a pattern like this. In this function, a cannot equal 0. If a equaled 0, then we would end up with canceling out this side of the equation because we're multiplying. Everything is going to be multiplied by that a value. So a can't be 0, and b right here has to be positive and cannot equal 1. This b factor right here, this b variable, is called the growth factor. I've labeled that for you down here. And it's the number, the value that's going to show how this function is growing exponentially over time. So that you need to remember that term growth factor as we move forward through the chapter. So there are two types of exponential functions, two special types. One is exponential growth, and that's the one we're going to talk about today on lesson 7.1. Exponential decay we'll talk about on lesson 7.2. So there are two types in the growth, which we'll talk about today. A has to be greater than 0. So we're talking about the a value, right here in the pattern. It's going to be greater than 0. And the b value has to be greater than 1. Okay, so that's how we're going to know whether it's growing or decaying. And you can kind of hear from those words that growth and decay sound a little bit synonymous with like positive slope and negative slope. It's kind of the same idea. It's the way that the function is going to grow and the way you're going to see it on the graph is going to be different. So let's look at number 1 and actually 1 through 3. We're going to need to match the function with the graph that is shown below, A, B, or C. And so what we need to spend a good amount of time doing on this part of the worksheet is making sure that we are evaluating our exponential expressions correctly. So let me get rid of this ink on the other side. And I'm going to come over here and I'm going to make a table for number 1. So f of x equals 4/3 raised to the x power, and then we're going to subtract 3 from that. So actually I meant to leave that right there. Should be an x. Okay, so now I'm going to go and make a table, and there are going to be some values that work a little bit easier for these exponents when you're raising that to a certain exponent. One of them often is going to be 0. That will work really well. If I take 0 and I plug it in here for this exponent x, we know that anything raised to the 0 power gives us 1. So anything raised to 0 power equals 1. So if we're talking about, a formula to keep in your mind, b raised to that 0 power is always going to be 1. So if we do that here, then we end up with 1, take away 3, that gives us a y of -2. The other exponent that is often easy to evaluate is 1. So we know that any exponential expression raised to the first power is just that number itself. So if we do that, then we end up with 4/3 minus 3, which will give us a -5/3. Okay, and so then if we come over and look at our graphs, we're looking for 2 points on a line. 0, -2, and 1, -3, 1, -5/3, which that lines up with our C over here. So we can see those points right here. So number 1 matches with the graph C. Do the same thing again with function 2. We'll make our XY table. And again, we'll try x of 0 and x of 1. X of 0 is going to, 3 to the 0 power will be 1, plus 2 is 3. And then 3 to the first power will just be 3 itself, plus 2, which will give us 5. Come over and match those points, and we can see those points right here on graph A. So number 2 is going to match with the graph A. So obviously 3 we would expect to match with letter B, but we'll go ahead and do the math for that one as well, just to double check it. And this one is a little bit harder to evaluate. So even though we pretty much know the answer is going to match with B, let's just pay special attention to this because it's the first one that we have a binomial as our exponent. So we're not just raising it to x, we're raising it to x plus 1. So the process doesn't change. We just need to be a little bit more mindful when we're plugging in our x's. So we're going to go ahead and try 0 because 0 will give us 1 as an exponent. So 0 plus 1 up here, that will give me -4 raised to the first power plus 1, which would be -4, which would be -3. Okay, and then instead of using 1, which I used 0 and 1 on the first two problems, however, if I plug in -1 right here, that will zero out the exponent. So if I evaluate x at -1, -1 plus 1 is 0. -4 raised to the 0 power gives me 1. And then I can say 1 plus 1 is 2. Actually, let me back up a minute and show you the evaluation on that because I actually just made the very mistake that I am hoping you guys will avoid. So let me write it out. So -4, and here's the deal there. That is the opposite of 4. That's not in parentheses. So if you think about it, this exponent is only raising the 4 to that power. So again, I'm still going to use -1. That's not where I made the mistake. The mistake was right here. The 4 is being raised to that 0 power, not the -4. If it were -4 being raised to the 0 power, and we've talked about this plenty of times in class, it would look like that. That's the whole entire integer being raised. This would equal 1. However, if the 4 is the only thing being raised to the 0 power, then that means the 4 becomes 1, but we're talking about the opposite of 1. So this is -1 plus 1, so we end up with 0. So my y value up here would be 0. Then we come back up here to the graph and we can see that those points do in fact line up with letter B. So now for this function, just like all of the other functions we have talked about, there's always a parent function, the most basic type of the function. So for an exponential growth pattern, an exponential growth function, this would be actually this would be the parent function. Okay, so this is the parent function on an exponential growth function. B has to be greater than 1. That's just a definition of growth. So the B value will be greater than 1 on a growth pattern. That'll change on a decay, which we'll talk about tomorrow on the next video. This pattern right here is if it's going to shift, if we're going to translate at all. So remember, translating means horizontal shift. So the h value, just like it has in all the other functions that we've done this year, The h variable shows you your horizontal shift. The k value is your vertical shift. And the a value shows your shrink or stretch. So it works the same on this function as it has on all the other ones we've done this year. The x minus h, that's written as a difference. The k, the plus k, is written as a sum. So the same patterns are going to apply to this function as well. So when we go over to number 4 and they ask us to graph the function, we're going to make an xy table. And on this one, I'm going to evaluate in at x of 1. And I'm also going to do x of 2, because we can see right here, if I put a 2 in for that x, 2 minus 2 gives me 0. 4 raised to the 0 power is 1. So that one I am done with. I did that in my head. 4 raised to the first power here would give me 4 to the negative first power. So that would look like this. And I'm just going to reciprocate that to get rid of the negative exponent. So 1/4 would be my value there. And arguably, what might have been even a better value to choose would be 3. Because if I evaluate 3 in for x, 3 minus 2 is 1. 4 raised to the first power is the number itself. So then I have 3 and 4, and I don't have to deal with trying to graph a fraction. So let's use 2 and 1 and 3 and 4. And I'm going to go ahead and do 1 here as well with that 1/4. Now, the other thing that before we graph this that we need to talk about is something called an asymptote. And these functions will employ something called an asymptote. And what that means is there's a line that this function is going to approach but never cross. So in this case, because our k value up here, I'm going to go in and write in that plus 0. It's not there. You know, our k is 0, which is why it isn't there. Our k over here in number 5 is 1. Again, in number 6, the k is 0. It's missing. We have an exponent up here of x plus 1, but there's no k value. Same thing with our problem right here. We have an h value of 2, letting us know that there's going to be a horizontal shift of 2 units to the right, but we don't have, our k value is 0. So what that means is that our asymptote is at y equals 0. Okay, so we have to keep that in mind, because there's a line here that our function approaches but is never going to actually cross it. I'm going to change colors here so we can see the line a little bit better. But it's going to take this curved shape and it's going to approach y equals 0, but it's never going to go underneath that. It'll just get closer and closer and closer to 0 as the x's get more negative, but it's never going to actually cross over the y equals 0 line. So the other thing we have to consider is domain and range, because they asked us to state that in the directions. You can see that all x's are going to be valid for this function, so we'll say all reals. Our range, because that asymptote is at y equals 0, that means all of our y's have to be greater than 0. And before we move on, let me go ahead and define asymptote over here. You can read about it on page 478 in your textbook. But the definition, and I'm pulling this straight out of the book, is a line that a graph approaches more and more closely. So the idea they're trying to convey to you there is that it's just going to get closer and closer while never actually crossing it. All right, we'll do our XY table For number 5, I'm going to evaluate at x of 0 and x of 1. So I'm going to plug 0 in here for x. That's going to raise 2 to the 0 power, which is 1. 1 plus 1 is 2. If I plug 1 in for x, 2 raised to the first power is 2. It's just the number itself, plus that extra 1 is 3. So we'll plot it 0, 2, and 1, 3. And again, we have to look at that k value, because in this case, this is the whole function shifted up 1 unit. That's a vertical shift up 1 unit. So what that means then is that the asymptote shifts from y of 0, it shifts up 1 unit to y equals 1. So the asymptote on this one is y equals 1. So the line, when we draw it, it's going to approach y equals 1. It's going to get closer and closer to it, but it's never actually going to cross. So domain on this one, again, is all reals. And the range, now we can see that our y's can't go under that asymptote of y equals 1. So we're going to say y has to be greater than 1. All right, and I got rid of all that ink so we have a little bit more clarity for number 6. XY table again. All right, on this one, as we determined before, we have x plus 1, so we have a horizontal shift of 1 unit. This would be 1 unit down, because that has to be written as a difference problem, but we don't have to really think about it, because when we sub in our x values, it's going to take care of the shift for us anyway. The other thing I want to point out, though, is that your value here, that is really an a of -1. So if you remember, the pattern looks, whoops, no parentheses, looks like this. All right, so our a value here, it works just like all of our a values have worked in the past. Same idea anyway. This is the shrink or stretch. It also tells whether it's going to be inverted or not. So because that a is -1, because this is really, this function over here is really y equals -1, 3x plus 1. All right, so we've got that -1a value. This is going to be flipped over, so this is going to be inverted. You'll see when we graph it, but I want you to be aware of that because it's going to take a little bit of a different shape here. So I'm going to evaluate in x of 0. So if I put x of 0 in here, I end up with 0 plus 1. That gives me 3 raised to the first power. Again, this is the same as the one I did earlier. This is -3 raised to the first power. And so because we're raising the 3 to the first power, and then that opposite of, so this ends up being -3 itself. And then we'll do the same thing with x of -1. So -3 raised to x of -1. You can see there we're going to end up with -3 raised to the 0 power. Okay, but once again, it's 3, it's the opposite of 3 raised to the 0 power. So the 3 is going to become 1, but we want the opposite of that. So we end up with a -1 here. 0, -3, -1, -1. And so now you can see that the line is underneath the axes, and it has taken on a little bit of a different curved shape. So our k value, once again, is 0. So that means that our asymptote is at y equals 0. So that's right here. That's the x-axis. Okay, so because that's our asymptote, this line here is going to approach it but never cross it. And so we're coming this direction. Sorry, that is a really bad line. Go the other way. We're going to be approaching y equals 0, but not ever crossing it. So the asymptote on this one is y equals 0. And that means that our, our domain is all reals. And the asymptote affects the range. So the range will be y, in this case, less than 0. So here are the steps for graphing these problems. Make a table and choose definitely 2 points, 3 points. What might help a little bit more until you get used to the way these curve. Evaluate those points and then plot them. After you have them plotted, go back to your function and identify your value for k. Remember, if it's not there, if there's no k value present, then it is 0, just like in all of the other functions that we've ever dealt with. Then step 5, draw your asymptote in. That will draw it in dotted. It'll be a horizontal line running through whatever that value of k is. Whatever you've determined k to be, run a horizontal dotted line through that point. And then go ahead and, using the asymptote and looking at the points, graph in that curved line and make sure you allow it to approach the asymptote but not cross it. Now, number 10 is a word problem about compound interest. And so whenever you see the word interest and compounded in a word problem, this is your formula right here. And we're going to use that formula. I'm going to show you how to use that formula for this problem. We need to identify the variables here. So A stands for the account balance. So that means, how much is actually in the balance currently. Okay, and this is what they're actually asking us for over here when they say find the balance after 1 year. So the account balance, how much is in it? P is what we call principal. And the principal is the amount of money that you deposited into the bank. So that's the principal. So in this case over here, our P value in this problem is $3,500 right here. They say you deposit $3,500 into an account. R is the interest rate. Now the thing about the interest rate is that they're going to often give it to you in percent, which makes sense. Over here you can see that they've identified it as 2.5%. But when you plug it into this formula, you need to plug it in as a decimal. So that means we're going to have to, just convert the percent to a decimal by moving the decimal place over 2 spots to the left. Okay, so we'll do that in a minute here. N is your number of compounding periods. And so what that means is how many times are they going per year, in this case, are they going to compound your interest? Are they going to add it in? So in number 10, they asked us to find the balance after a year if the interest is compounded with the given frequency. So that's what N is. It's the number of compounding periods. It's the frequency with which the interest is going to be compounded. If it's only compounded annually, well then after 1 year, it's only been added in 1 time. So our N in this case on number 10 is 1. We're not going to do 11 and 12 on the video, but if we are looking there quarterly, that means quarterly means 4 times per year. So that would be an N of 4, and monthly, of course, would be an N of 12. So those values are going to change depending on how often, the frequency of which the interest compounds. And then T is the number of years. So the number of years you've had the money in the account. So if we're going to fill in all of that information for number 10 over here, then it would look like this. They're asking us to find the account balance. That's what they say, find the balance. So that's A. They told us our principal was $3,500. Right, put my parentheses in. That 1 is a constant. It stays there. It's not ever going to change in this formula. I'm going to add to that the rate, the interest rate divided by the number of compounding periods, R divided by N. Well, my interest rate is 2.5%. So if I want to convert that into a decimal, it's going to be 0.025. I'm just moving the decimal place to the left twice. and then I'm going to divide that by my n of 1. And then the exponent, which is why this is an exponential function, is n times t. So my n is 1, my t is also 1 in this problem because they asked me to figure it out after it's only been in there 1 year. Of course, this would be different if they were saying find the balance after 2 years, then I would have 1 times 2 up there as my exponent. All right, so then we just need to do our algebra to solve this problem. All right, this is going to be 1 plus 0.025. All right, so anything divided by 1 here is just going to be 0.025. So I'm going to just do that in right here, and then that's obviously going to be raised to the first power, which I don't even need to write anything in there because the exponent 1 doesn't have to be written in, it's always assumed. So there's your equation right there. Get out the calculator, multiply the two of those together, and you will get a balance of $3,587.50. Oop, that's supposed to be a decimal. So that means after 1 year, if you put $3,500 into an account that accrues at 2.5% interest, at the end of the year, doing nothing else, putting no other money in, you would have grown your account by $87.50 just in that, as that interest compounded. You're going to need this, all this information over here for future problems, so make sure that you have this written down either on this worksheet or in your notes somewhere where you're going to be able to get back to it, because if you know what each of these variables stands for, and you already have an example worked out here, it's going to be a lot easier to do this on future problems. Now 13 through 15 are using a slightly different model. This is called the growth model, and it is different in the fact that this is a growth model. The one we just did was based on compounding, the growth rate changing multiple times over a certain period. This growth model, you can see in the word problem, you're looking kind of for that keyword compounded to know whether you need to use the previous function. You don't see that in this word problem. So this is just a simple growth model where here they're saying over a 10-year period the population of California was modeled by this function right here, this exponential function, where t is the number of years since 1990. So this is following this growth model. It is still an exponential function because you can see that the parentheses here, 1 plus r, is being raised to the t power. Okay, so in this case, the variables stand for a lot of the same things that we had in the first function up above. A is going to be the initial amount. So in this case, that would be the initial population of California in 1990. And then the R is your percent increase. Again, we're going to want this written as a decimal if it's given to us in another way. And then T is the number of years that we're talking about the growth happening. So in this case, this is a 10-year period. And so anywhere in there, if they asked us to find the growth or the population in 1993, well, we started in 1990, we're going to 93, that's 3 years, so that's a t of 3. So if we use this function right here for that they gave us to answer the first question, what was the population in 1990? Well, 1990 was the very first year that they did this. So 1990, take away 1990 gives us 0. So we're talking about that we haven't even completed a full year yet. So we would sub in 0 for our t right here. So that would become 0. We know anything raised to the 0 power is 1. So this whole thing becomes 1 multiplied by the initial population, tells us what the population was in 1990. Okay, so it just matches this A value right here. So let's go down to 15. We're actually going to skip over 14 for right now. Estimate the population in 2007. So we're assuming, of course, that the rate this model is still going to model the population of California and its growth. Um, and so if we're going to assume that, then we'll continue to use the function they gave us in the problem. And what's going to happen, though, is our t is going to change. Oh, that's supposed to be 1. So our t is going to change to 17 because the number of years between 1990 and 2007 is 17. So we've got that exponent there. Now from here, there are two ways that we could solve it. The first way is we could just evaluate into our calculator this number right here, raised to the 17th power, hit your enter sign or your equals, and then multiply that answer by our initial population. Okay, so that's one way to do it. The other way to do, and if you do it that way, then you end up with 37,013,552. So try in your calculator, evaluate that, and make sure you get that number so that we can determine whether you're evaluating this exponential expression correctly or not. That way, if you're not getting that correct answer, you can ask a question in class, in our next class. The other way to do these problems is to graph them on the calculator. So you would actually, just like you normally do, you would go to y equals on your calculator. You would plug in this function right here. So instead of p equals, you have y equals. Plug that function in. Where it says t, you're going to actually just hit the x button, the variable button, just like you have been doing for all the other functions. Again, remember, it doesn't have to be the letter t. It's okay for it to be the x. And then you'll hit your graph button. So you're going to go to y equals, plug in your function, and then go to graph. So these two steps are the same that you've been doing for all the other graphing. Then after you've done that, you'll hit the trace button. And we haven't used the trace button a whole lot, but the trace button, what it allows you to do is trace up and down the line of the function. It'll keep your cursor right on that line. Now you may need to change the window on the function in the function box, because if you look here, you're going to get some very large y values. Your x values, or in this case your t, in this function, they're not going to be that large. I mean, you're going to t of 17 here, from 0 to 17. So go, if you're not seeing your graph once you come here and graph it, then go and change your window. So try changing your window to what I have right here. This y, the range, taking it up to 40 million, should allow you to be able to see the answer, and it should be fairly clear. Once you have that window and you're seeing the graph, then you go to the trace button and just use the trace button until you get to x of 17. That corresponds to 17 years after 1990, and that should yield you a y value that matches this population that we see here. So try that on your calculator, because those are two ways to do it. And you wouldn't want to take the time to graph these out by hand. That would, of course, be too lengthy of a process and not very accurate. So you're going to want to be able to use your graphing calculator for problems like this.